Hello, everyone, and welcome to the second session on OSP Pulse. Yeah, let's continue and already explain together this book. Okay. Yeah. Today we will already continue on this book, Android system programming, porting, customization, and so on. This is chapter one is all about giving you a big picture view of Android system programming, what it is, and why it matters, and how it fit into the world of embedded and automotive system. I think this chapter started with a discussion on system programming in general, then zoom in an Android's unique approach, and you will get an overview of the Android system architecture. Think of this as a map showing all layers from the Linux kernel up the app framework, and this chapter also introduces the third-party open source projects you will use throughout the book. And I will try to ready to handle and practice this is on the cuttlefish and emulators, and maybe on the Qualcomm board and Raspberry Pi. There are the real tool and the libraries that make Android system work possible. And I think also covers some virtual hardware platform, basically how you can test and develop Android system even if you don't have real hardware in your desk. So what you will cover in this chapter is what Android system programming and the main layers and the components of Android architecture, the third-party projects and tools you will use for hand this on work and so on. So how to use virtual hardware platform for development and testing. I think this is already the brief about the what we will do today. So this is first. So, system programming here is all about writing software that interact closely with the core part of computer system, saying operating system, device driver, and low-level utilities. And the main goal is to create software that provides services to other software or directly manages hardware resource like CPU, memory, and the devices, and so on. In the context of Android, system programming means working with the building blocks under the hood. The Linux kernel has system services and the Android framework. Unlike classic system programming, like in Linux or Windows, Android system programming often focuses more on customizing the OS for specific hardware, adding a new feature, or optimizing performance for embedded devices like automotive infotainment system, IC, and so on. Okay, and books like Linux system programming or Linux device drivers are great for understanding the basic, and but Android adds its own layer like Binder IPC, AIDL, and the health that you need to learn for real world projects. And in practice, Android system programming is about bridging the gap between hardware and user-facing feature, making sure everything from sensor to display works smoothly and securely. Okay, let's move to another. So, what is the scope of this book on Android system programming? The book focuses on practical Android system programming, especially how to customize and port this Android system to new hardware platform. It drew a line between application programming, Java, Kotlin, a player, and the system programming, C, C++, HAL, kernel, low-level system services. And the main audience is engineers who want to understand and modify the lower layers of Android, like kernel, HAL, and the system services, not just app developer. Okay, and the book doesn't spend much time on the Android framework, which Google changes often and so on. But instead it dives into porting OSP Android open source project to different hardware. You will learn how to adapt Android for new boards, what needs to change in the system, and how to handle updates like OTA over the air updates and so on. And this approach is hands-on with real projects and examples, not just theory. Okay, and we can say if you want to know how to bring up Android and new hardware, customize the OS, and understand what is happening under the hood, this book is for you. Okay, and yeah, we will explore together the next one. Yeah, let's move. Here's the main focus when porting or customizing Android system is on the layer below the application framework, specifically the kernel and the hardware abstraction layer. Yeah, most real-world Android system work, especially for vendor and the OEMs, is about adapting this lower layer to a new hardware, not just writing apps. When Google releases a new Android version, vendor must port it, their hardware, by customizing the reference platform like Qualcomm and so on. This means updating the kernel, HAL, and sometimes system services and so on. So the book highlights that this knowledge also applies to Android derivatives like wearable and maybe we can say Android things and so on, which is Brillo. And we can say also this is lightweight Android OS for IoT devices and so on. So the architecture diagram on the screen now show that both Brillo and Android share a similar structure. Hardware at at the bottom, then kernel, then HAL, and so on, as you see now. Okay. Yeah, yeah. As you see at the bottom, yeah, we have hardware, then kernel, then HAL, and so on, and finally system services and application framework at the top. Okay. Yeah, for both Android and Brillo, porting work is concentrated at the kernel and the HAL layers. These are the glue between hardware and the rest of the system. So Brillo is just a stripped down version of Android for IoT, but the porting process is fundamentally the same. So we will on this we will walk through a real example of porting the HAL of for new automotive sensor, or explaining how kernel changes impact the rest of the Android stack. Just let yeah, this is we will discover together. Okay, let's move to another one. This so the question here: what are the main architectural layers of Android system, and what are some key kernel customization in Android? So we can say the Android system is built in layers, application framework, where app developers interact, activities, surface, and so on. And Android system surfaces and the HAL, this is the system level surfaces and the hardware abstraction layer, which lets Android talk to the hardware in a device independence way. And we have also the kernel. This is the foundation based on Linux, but with Android specific changes. We have also Binder IPC is a core part of Android used for secure and efficient communication between processes. You can think apps talking to system services and so on. So Android kernels now, what can we say about the kernel? As we mentioned above, already the foundation based on Linux, but with Android specific changes. And Android's kernel is not just vanilla Linux; it is customized for mobile embedded needs. Okay, like ashmem, and this is let's app share memory efficiently, like Scratchpad for fast data exchanges. And we have also the binder here. This is inter-process communication. This is the main way process communicate in Android, acting like a secure post office for messages. And we have also the logger. This is optimized logging for lots of small logs, right, crucial for debugging and so on. And we have also this is paranoid networking. Yeah, this is extra security to restrict which process can access the network. And we have pmem, so this is a physical memory. Yeah, this is big chunk of physical memory to user space, often for things like camera or graphics buffers. We have also another like Viking Killer. This is also Android's own DOM killer, and yeah, tuned to kill the least recently used apps when memory is low and so on. This is Viking Killer, okay, and in the respect wakelocks and so on. So yeah, well, what we can do here, yeah, we can say this is customization make Android kernel better for devices where memory, security, and the power are critical, like phones, IVI, and embedded system. So in real projects like infotainment system or Android Automotive OS work and so on, you will often need to touch these areas, especially binder, HAL, and sometimes kernel drivers, maybe kernel bring them and bootloader bring them and so on. Okay, let's move to to next. This is one. Yeah. So Android kernel development, here we can say most Android devices drivers are similar to standard Linux device drivers. Okay. So if you can write a Linux driver, you can usually port it to Android with little change. And the main difference is in power management, wakelocks, and some Android specific patches. Yeah, Android kernel source is often provided by SOC vendor like Qualcomm, like MTK, and so on. So and the Google reference kernels are open source. Different SOCs have their own kernel trees, like Qualcomm. This is under, I think, kernel SM and so on. This is, and I think Mediatek under kernel or also Mediatek and so on. But the base Android kernel is in kernel common. Okay. So the default OSP kernel is for Google devices, but there are also reference boards and open source projects for other architecture like x86, and merges from mainline Linux to Android are tracked, and you can check release notes to see what is new or different and so on. I will share also the link from Google. And yeah, when working on Android automotive or infotainment system, you will often deal with the vendor kernels and need to understand which patches are Android specific, like wakelocks versus standard Linux. Always check the vendor's kernel tree and compare it to kernel common for differences and so on. Okay, so so our question now, what is the role of HAL and Android system services in the Android architecture? So the HAL, it is hardware abstraction layer, act as a bridge between Android higher level system and the device's hardware. And it lets hardware vendors implement feature without it changing the Android framework. And has also, we can say, are usually shared libraries .so files loaded by the system when needed, and this makes Android agnostic to the details of the hardware. And so the same Android code can run on the different devices as long as the right HAL is present. And in real projects, you will often customize or debug HALs when porting Android to new hardware or adding features like a new sensor or custom audio chips and so on. And the next one, Android system services. This is our core services running in the system server process. So like window manager, notification manager, and so on. And they expose API to the applications and manage access to hardware and the system resource. System services already talk to HALs to interact with the hardware, and so app don't need to know hardware details. And there are also media services for audio, video, and other daemons for surface flinger for graphics. In embedded work and automotive, so you will often extend or debug these services to add new feature or fix integration issue. You can think of HAL as a translator between Android and the hardware, and the system services as a manager that app talk to the for everything from graphics to notification and so on. And this separation is what makes Android so portable and modular. Hardware changes don't break the app layer, and the new features can be added cleanly and so on. Yeah, I think this is also in the through the book you will see real example of customizing a HAL or debugging system services and so on. Yeah, let's move. So, what is a Binder IPC and how does the application framework interact with the system service in Android? So let's start with the Binder IPC is Android's main way for different processes to talk to each other, especially for app to talk to the system services, as we mentioned before. Think of Binder like a super fast, secure that deliver message between apps to and the Android system, even though they run in separate sandbox process. Okay, so the application framework is a set of APIs that developers use, and when an app needs something from the system like location, camera, it calls a framework API. And under the hood, this framework API using Binder IPC to send the request to the system services and so on. Yeah. Okay. Yeah, the system services which actually do the work like talking to the hardware or managing resource and so on. This separation, this separation keeps the app secure and stable. Since they cannot directly access system resources, they have to go through the framework and the binder. Yeah, I think also you can imagine the application framework as a receptionist as at a big company, and if you or the app want something from the building the system, yeah, you ask the receptionist framework API. This is a receptionist. You can already imagine it as a framework API. So the receptionist uses this company's internal mail system Binder IPC to send your request to the right department system services, and you never get to walk into the server room yourself. So everything goes through official channels and so on. Okay. Yeah, I think our question here, we what it matters in interviews. Yes, I think so. Yeah, I need you to show your understanding Android security and architecture, and the great candidates mention why Binder is used, security, process isolation, performance. You can also stand out by giving real example. For instance, when I extend this Android Automotive OS framework with the custom VHAL properties, I used Binder IPC to let the app layer communicate with the new system services. And yeah, there's some pitfalls. So don't just say Binder is for IPC. Explain why Android needs it. And don't forget the application framework is more than just libraries. It is the whole API, okay? That sits on top of the system services. So we can already go quickly, yeah, to avoid more time. Yeah, now we need to ask ourselves about new questions. What is Android recovery and how does it work compared to the main Android system? So, Android recovery here is a minimal self-contained system used for upgrading, reinstalling, or repairing Android devices, and it is a part of OSP source code. You can get it at OSP Potable Recovery, and recovery runs on the same Linux kernel as Android, but it's a separate environment. Think of it as a mini OS just for maintenance. And when you boot into recovery, the device loads a special partition with its own RAM disk and tools, not the full Android system. And you can say the recovery is used for tasks like flashing updates, factory reset, or unbreaking devices, especially useful in automotive or embedded deployments where field recovery is critical. Uh, yeah, in your work, you might use or customize recovery for safe auto A updates or to provide robust fallback options for infotainment system and so on. Yeah, in you can imagine recovery as a car services mode. Even if the main dashboard is dead, a mechanic can still access this mode, and to fix or update the car's software and so on. So, in the interview, you can also recovery is separate from the main Android OS, but shares the kernel, designed for reliability and single purpose task, update, reset, repair, and so on. And yeah, also, great candidates here. You can mention how recovery improves the device robustness and support field maintenance and so on. If you want to already, if you want, and you need to already dive into how recovery is built and how to customize it or how to interact with the partition and the bootloader, you can just yeah, give me the comments under the video so we can already discuss it. Yeah, as you see now, this is a typical Android GPT partition table showing how storage is split into different sections, each with specific jobs. And the recovery partition is one of the most important for system reliability. It holds the recovery RAM disk, minimal OS environment, separate from the main Android system. When you put into recovery mode, the device loads this RAM disk, which has a directory structure similar to a normal root file system. And the init script in the recovery RAM disk starts the recovery program, which becomes the main process for that mode. And the recovery is used for tasks like system update, factory resets, and repairs. It is specifically also, or oh yes, specifically and especially critical in automotive and embedded systems where you need a reliable way to recover or update devices in the field. So programming for recovery is just like writing native Android daemons, the same language, same debugging tools, and the same development flow. And the separation of recovery into its own partition means that means that if the main system is corrupted, you can still put into recovery to fix or update the device. And this design is a big reason why Android devices are robust and maintainable, especially in demanding environment like automotive. Yeah, I think maybe we can read enough here. Let's check. Yes, I will stop here, yeah, to avoid a lot of time in this video, so we can already satisfy it here. So see you in the next OSP Pulse. Thank you so much. Bye bye.